For our project for ECS 2210, our group, consisting of Dennis, Josh, and Delan, decided to build a ripple 2-bit adder using transistors. The circuit is capable of taking two inputs of 2-bit numbers and computing their final sum. In order to do this, the adders we created are composed of logic gates built from transistors. Overall, the total transistors used in our circuit is 44, and the total resistors are 70. The logic gates that our adders are composed of include NOT gates, AND gates, and OR gates, whose circuits are illustrated here. The complete adder circuit is shown here, but this demonstrates only one bit. As shown in red, we have the main currents that are passing through the circuit based on the specific conditions regulated by the logic gates. Here we have a simpler illustration of the ripple adder so that we can explain its functionality in an easy-to-follow manner. The ripple adder shown below functions from the right to the left, where the A's and B's represent the inputs, the S's represent the sums, and the C's represent the carry. To begin with, C0 has no input, as there is no carry in the beginning of the circuit. A0 and B0 are then both added, computing to S1 and C1. For example, if A equals 1 and B equals 0, the sum is 1 and the carry is 0, while if A equals 1 and B equals 1, the sum is 0 and the carry is 1. This C1 then gets carried over to the next portion of the circuit, the second adder, and is added to the inputs A1 and B1, where once again the sum and the carry are being outputted based on the corresponding inputs. Here is a demonstration of our circuit.
Alright, so this is our circuit for ECS 2210. So for this circuit we decided to build a 2-bit ripple adder. So we have two unique adders in the circuit. So this is the first adder and then this is the second adder. Pretty much how it works is we replaced the logic and OR and NOT gates with equivalent transistor-based gates. So this is one full adder, and pretty much how it works is depending on your A in and your B in, the current flows through the various transistors, amplifying it and turning off and on the transistors like switches. It then goes through the second circuit and does the same thing with the addition of a carry in. And when you're doing that, you add up to turn on these various different lights depending on which switches you have on. So the sum would be a total of 1 plus 2 plus 4, so a total of 7, and any variation in between those. So we'll start off by trying the first one. And you see when you turn that on, it turns the first LED on, so that's a sum of 1. And then you turn the second one on, you get a sum of 3, so that's good. And then on the next one, if we want to turn all of them on, right? There we go. So now you have A and B plus the original one on, so that's a sum of 7, so 1 plus 2 plus 4. And if you wanted to turn, let's say, just this one and this one on, well, I guess we'll do 6 first, so we could just turn that off and we get to 6, back to 7, turn this off, we can get to 5, and then that's pretty much all the various different variations of it. If you want 4, again, you turn that one off, and that's pretty much how the circuit works.
Adders are crucial to much of computing, and therefore there are many applications of adders in processors and computers. Often used as arithmetic logic units, ALUs, they are very apparent at the operating system level for address table calculations and incrementation. As our adder is only 2-bit, it can only calculate up until the binary 111 or 7, as explained in the demonstration. But full adders are typically components of a cascade of adders, which add 8, 16, 32, and so on bit numbers.
The following slides are our calculations for the transistor NOT, AND, and OR gates. The transistor in the NOT gate is in cutoff mode when there is a positive voltage applied. The transistor in the AND gate is in the active region when both inputs are applied, and the output is a positive voltage if both inputs are positive. Lastly, the transistors in the OR gate are both in the active region due to positive input voltages, resulting in a positive output if either or both of its inputs are positive. Thank you for watching our presentation.